1 we have to find linearization. F of 1 1 becomes 2 into 1 square plus 1 square equal to 3. Because our function is 2x square plus y square, we substitute the value of x0 y0 in our function. We get f of 1 1 is equal to 3. If we find partial differentiation of f with respect to x at the point xy, we get fx xy equal to 4x. Similarly, partial differentiation of f with respect to y at xy, we get fy at xy equal to 2y. So, fx at 1 1 become 4 and fy at 1 1 become 2. So, now we know that equation of linearization for function of two variables Lxy equal to f of x0 y0 plus fx at x0 y0 into x minus x0 plus fy at x0 y0 into y minus y0. If we substitute our all the values, we get is equal to Lxy is equal to 3 plus 4 into x minus 1 plus 2 into y minus 1. So, linearization function for two variable Lxy becomes 4x plus 2y minus 3 by solving that. The linearization of f at the point 1 1 is becomes Lxy equal to 4x plus 2y minus 3. In that case, our function f of xy is approximate as 4x plus 2y minus 3 is called the linear approximation or tangent plane approximation of f at the point 1 1. Similar example, find the linearization of f of xy equal to x square minus 2y plus 1 by 2 y square plus 3 at the point 3 2. Our function is here x square minus 2y plus 1 by 2 y square plus 3 and our point is 3 2. Here first we evaluate f, fx and fy. Just partial differentiation of f with respect to x with respect to y at the point x0 y0 equal to 3 2. Here our f of xy equal to x square minus 2y plus 1 by 2 y square plus 3. So, f of 3 2 becomes 8. By substituting value of x0 y0 equal to 3 2 in f of xy, we get its value 8. Now by differentiating f with respect to x, we get fx equal to fx at xy equal to 2x minus y. So fx at 3 2 equal to 4. And since fy equal to minus x plus y, so fy at 3 2 becomes minus 1. Now we know that the linearization for function of two variable, the formula is Lxy equal to f of x0 y0 plus fx at x0 y0 into x minus x0 plus fy at x0 y0 into y minus y0. By substituting all that values in that equation, we get the linearization of Lxy. We are equal to 8 plus 4 into x minus 3 plus minus 1 into y minus 2 is equal to 4x minus y minus 2. So, the linearization of f at 3 2 is Lxy equal to 4x minus y minus 2. Now we see here for function of three variable, how can we find linearization of the function? We have the example. Find the linearization Lxyz of f of xyz equal to x square minus xy plus 3 sin z. Here our function is function of 3 variables. So how can we solve? We see here. Here f of xyz is x square minus xy plus 3 sin z. So at the point 2, 1, 0, we get f of xyz equal to f of since f of xyz equal to x square minus xy plus 3 sin z, if we put 2, 1, 0, we get f of 2, 1, 0 is equal to 2. Now if we differentiate f with respect to x partially, we get fx at xyz is equal to 2x minus y. So at 2, 1, 0, our fx becomes 2. Similarly, fy at xyz is equal to minus x. So fy at 2, 1, 0 becomes minus 2. And our fz at xyz equal to 3 cos z, fz as at 2, 1, 0 become 3. Now linearization for function of 3 variable, we have the formula Lxyz equal to f of x0, y0, z0 plus fx at x0, y0, z0 into x minus x0 plus fy at x0, y0, z0 into y minus y0 plus fz at x0, y0, z0 into z minus z0. If we substitute all that values in that equation, we have Lxyz equal to 2 plus 3 into x minus 2 plus minus 2 into y minus 1 plus 3 into z minus 0. By solving it, we get it is equal to 3x minus 2y plus 3z minus 2. Now the other application is partial derivatives with constrained variables. There are two types. We see type 1. How to find del omega by del x when the variables in w equal to f of xyz are constrained by another equation. We use following steps. The step 1 is decide which variable are to be dependent and which are to be independent. First. Now second is estimate the other dependent variables in the expression for omega. Third, differentiate as usual. And our type 2. If we can't decide which variables are dependent and which variables are independent, then we differentiate the equations as they are and try to solve for del omega by del x afterward. Here we can see one example. We want to find del omega by del x at the point 1, 1, 1. And our omega is given that omega equal to x square plus y square plus z square. And the other equation is z cube minus xy plus yz plus y cube equal to 1. And x and y are the independent variables here. Now we solve it. It is not convenient to eliminate z in the expression for omega. We can see in equation number 2, z cube minus xy plus yz plus y cube equal to 1. So in that expression for omega, we differentiate both equations implicitly with respect to x, treating x and y as independent variables and omega and z as dependent variables. So we get del omega by del x equal to 2x plus 2z into del z by del x. We say it equation number 1. And the other equation, by differentiating partially, we get 3z square into del z by del x minus y plus y into del z by del x plus 0 equal to 0. We say it equation number 2. Solving equation 2 for del z by del x we get del z by del x equal to y by y plus 3z square. Now substituting values of del z by del x into equation 1, we get del omega by del x equal to 2x plus 2z into y by y plus 3z square. So is equal to 2x plus 2yz upon y plus 3z square. So the value of del omega by del x at the point xyz equal to 1, 1, 1 is del omega by del x at 1, 1, 1 equal to 2 into 1 plus 2 into 1 into 1 by 1 plus 3 into 1 square equal to 5 by 2. By substituting all that values in our equations, we get that. Now other example, find del omega by del y where x and z constant. If omega equal to x square plus y minus z plus sin t and x plus y equal to t. Now we solve here it. With x, y, z independent variables, we have here two equations, t equal to x plus y and omega equal to x square plus y minus z plus sin x plus y. Now del omega by del y at xz constant equal to 0 plus 1 minus 0 plus cos x plus y into del by del y of x plus y. By differentiating partially of omega with respect to y, and our x and z variables become constant. So we get del omega by del y at xz constant is equal to 1 plus cos x plus y into 1. Now the other application is Taylor's expansions for functions of two variables. Now Taylor's expansion is the one of the important application of partial differentiation. Now we know that we have learned Taylor's theorem for a function of a single variable in the form f of x plus h equal to f of x plus h f dash x plus h square by 2 factorial f double dash x plus h cube by 3 factorial f triple dash x plus up to so on. Here we will say it equation number 1. Here we treat f of x plus h and y plus k as a function of a single variable x, and using the equation 1 we have f of x plus h y plus k equal to, because of our x is only the single variable and y is treating as constant, so y plus k remains as it is. So is equal to f of x y plus k plus h f dash x y plus k plus h square by 2 factorial f double dash x y plus k plus h cube by 3 factorial f triple dash x y plus k plus up to so on. Here we see that the application of partial differentiation, here f dash, f double dash, f triple dash are differentiating partially with respect to x. Now treating f of x y plus k as a function of y, we have f of x y plus k equal to f of xy plus k f dash xy plus k square by 2 factorial f double dash xy plus k cube by 3 factorial f triple dash xy plus up to so on. Here f, f dash, f triple dash are partial differentiation of f with respect to y. So in equation 2 we can say equation 2 takes the form f of x plus h y plus k equal to, by substituting all this equation in the ego equation, we get f of x plus h y plus k equal to f of xy plus k del f by del y at xy plus k square by 2 factorial del square by del y square at xy plus up to so on plus h del by del x of f of xy plus k del by del y of f of xy plus k square by 2 factorial del square by del y square at xy f of xy plus up to so on plus h square by 2 factorial del square by del x square into of f of xy plus k del by del y of f of xy plus k square by 2 factorial del square by del y square at f of xy plus up to so on. Now we can see that from that equation our f of x plus h and y plus k become f of xy plus h del f by del x plus k del f by del y plus 1 upon 2 factorial h square del square f by del x square plus 2hk del square f by del x del y plus k square del square f by del y square. We can say the other for third order 1 upon 3 factorial h cube by del cube f by del x cube plus 2h square k del cube f by del square x del x square del y plus 2hk square del cube f by del x del y square plus k cube del cube f by del y cube plus up to so on the other so on, which can be written symbolically as f of x plus h y plus k equal to f of xy plus h del by del x plus k del by del y at f plus 1 upon 2 factorial h square del square by del x square plus 2hk del square by del x del y plus k square del square by del y square at f. Our f is a function of two variables x and y, f of xy. Here we say that equation number 3. The equation number 3 is Taylor's expansion for functions of two variables.